All right, so tonight we're going to go over chapter 6A. Chapter 6, of course, is the last chapter of the course, and this chapter is about applications of integration. Now, some of these are going to be a lot more important than some of the others. There's several sections of this chapter that are basically physics applications, which, well, yes, they're kind of important, but I think we'll save those for last. And in fact, I'm going to make up a list of the topics that could potentially be on the final exam. And I think we may just go over the physics applications, but I think that we'll leave them off the final exam because, not everybody's interested in physics. And so we'll see how that goes. But right now, I've chosen the most important topics from chapter 6 to start with. So we'll start here with the integrals, exponentials, and logarithmic functions. And so we're going to dive more deeply into logarithms and exponentials, which means e to the x. And we'll see that these results are based on the fundamental theorem of calculus, and they provide us with more techniques that we can use to calculate both derivatives and integrals. So first things first, we say that if f of x is continuous, of course, as usual, the function must be continuous. And also it must be continuous over a closed interval a to b. You'll recall that the antiderivative is defined as what results is the function whose derivative gives us back equal to f of x. But we're seeing here for the first time a different way of expressing it. We can define the antiderivative as the integral of our function f of t over the interval from a to x. Okay, and so also don't forget that because capital F is the antiderivative, that implies that its derivative is the original function. Okay, so there's the antiderivative is the function whose derivative gives us back the original function. And this only has to be true over the closed interval from a to b. Now, by writing the antiderivative this way, it turns out that we can define the natural log ln x in terms of an integral. And we'll see in a second why that's true. But don't forget that, of course, ln x is simply shorthand for the log to base e of x. Okay, so the graph on the next page is going to show you why this definition does in fact reflect the integral of the log of x. And one more thing, notice that the lower limit of integration is 1 because the log of 0 is undefined. Okay, so here's the graph. So what they're saying, this is what 1 over t looks like. You can see that it falls off very, very rapidly, but both the horizontal and vertical axes are actually asymptotes of this function. And so the area under here is log x. In other words, if we chose this value, which looks like it's about 2.2 is our log, is our value of x, then whatever this area is represents the log of 2.2. Okay, so in other words, assuming that x is 2.2 here, although they didn't label it very well. If that's our 2.2, then the shaded area is in fact the log of 2.2. So that's why it's written this way. In other words, whatever x we've chosen, the integral is defined over that interval from 1 up to whatever x happens to be. And within that interval, the area under the curve is the value of log x. Okay, so it's written a little strangely, but that's what it's trying to tell us. The area between 1 and x under this curve is the log of x. Now, if x is less than 1, in other words, anything to the left of 1, then this no longer holds because the log of any number less than 1 is negative. So we have to replace this definition with negative log x. Okay, so in other words, suppose this value is, I don't know, 0.3. Okay, so that log is this whole area, but it's the negative. If you took the log in this range, you'll get a negative number. So we have to replace our area with negative log x. But from 1 up to positive infinity, this function, this relationship will always hold. All right, now, here's something we've already seen before. As long as x is strictly positive, the derivative of log of x is 1 over x. And by the way, here's an important result too. If a function is differentiable, which means that the derivative exists, it must be continuous. That guarantees continuity. It doesn't cut both ways, though. In other words, knowing that a function is continuous doesn't guarantee that there's a derivative, but knowing that there's a derivative guarantees that the function is continuous. The natural log is the antiderivative, as we've already seen as well, of 1 over u du. Okay, you might recall that it's the absolute value. So whatever u happens to be, when we take the integral of 1 over u du, or of course you could also write this as du over u, you'll end up with natural log of absolute u plus c. And of course, don't forget the c, because this is an indefinite integral. We always need the c with indefinite integrals. Now, here's something I don't remember if we probably went over this. I'm starting to forget already what we did in the first chapter. But as long as a and b are positive and r is some rational number, we know that the natural log, or any log for that matter, of 1 is 0. Because 1 to the 0, 0 to the 1. Is 0. Okay, now the log of a product is the sum of the individual logs. The log of a ratio is the difference between those two logs. And here, if it's the log of a raised to some rational number, and of course, don't forget the word rational simply means ratio of 2 integers. In other words, it could be something like 2, it could be 3 halves. Any integer counts. The ratio of 2 integers. What does not count, though, is things like pi. For example, pi is irrational, as we already know. But what's interesting, too, is that the square root of any number, just mention this as an aside, the square root of any number. Now, of course, it's understood we're talking about positive numbers or non-negative numbers. That is not a perfect square. Is irrational. So just a quick reminder, a perfect square simply means a number whose square root is an integer. So in other words, numbers like just quickly throw out a few examples here. Let's say 4, 9, 16, 25, 36. What do they all have in common? The square root of each of these numbers is an integer. The rest of the natural or counting numbers actually, what I should say is for the rest, such as 3, 5, 17, 22. The square root is irrational. Okay, so in other words, the only square roots that are rational are the ones where the number itself is a perfect square because the result is an integer. For all the rest, the square root is irrational. So in other words, this property does not hold for, let's say, if r is radical 3, that means this does not work. Okay, but for any rational number, the log of a to the r is r log a. And this proves to be a very helpful formula for simplifying results. Well, actually, they're all helpful. And so they can help us simplify results, especially when we're doing integrals. That's when it really pays for itself, because then we can take what appears to be a very messy expression and turn it into something that's manageable with one of the formulas that we know. All right, now, here's a good example. Now, this is a log, of course. What's going on here? Well, first things first, let's remind ourselves of the so-called generalized power rule. So all that means is that if you have some function of x raised to the nth power, the first derivative is n times g of x, that function of x, to the n minus 1 power, but then we have this g prime of x. All right, so in other words, you need that g prime of x, whereas if you started out with something simpler like x squared, then by the power rule, you have 2x to the 1, which is just 2x. But here, if you have, let's say, something like this, when you take the derivative, it's not enough to multiply the whole thing by the exponent and then reduce the exponent by 1. You also need the derivative of what's going on inside these parentheses. In other words, g prime of x. Okay, so whenever you are taking some function of x and raising it to a power, then you'll need to do something like this. You'll need to make sure that you're including the derivative of what's going on inside the parentheses. Anyway, so that's going to help us here, because you might remember, as we just explained, the derivative of log x dx is just 1 over x. But if it's not the log of x, but the log of g of x, that changes everything, doesn't it? So all of a sudden, we not only have in the denominator, we have this g of x, but we need in the numerator the derivative of g of x. Okay, so in other words, d log x, let's say it's d log 3x squared. We're going to have in the numerator, you'll have the derivative of this expression 6x, and then the denominator, you'll have g of x. And of course, in a case like this, you can reduce it to 2 over x. Okay, but the key here is that the numerator has to contain the derivative of what we're taking the log of, because it's a function of x. Here, we don't have to bother. Although technically we are doing that here too. It's just that the derivative of x is just 1. So we just write it as 1 over x. But in principle, we're actually applying the same rule even to just plain log x. It's just that you don't notice it because the derivative, like I said, of x is just 1. So anyway, so from our original problem, we have 5x cubed minus 2. So this is our g of x. And of course, based on the power rule, the derivative g prime of x is 15x squared. So in the next slide, we'll see that the result of this is very simply g prime of x, which is 15x squared. Down here, we have g of x, and we're all set. So logarithmic differentials are really very, very straightforward, which is kind of why we use them. If we're using a log with another base, that complicates things, as we'll see. But it's a very similar process, but we do need to do something a little different. So here we're sticking with the natural logs. Now here's another possibility. So we're going to use the power rule again. Think of this as g of x could be 3x Okay, so what are we doing? Oh, sorry. Oh, no, wait a minute. No, I'm doing it because this is squared. We're not going to do it this way. Hold on one second. We're going to do it something slightly differently. We're going to let g of x be the entire expression. Because this entire expression is being squared. So this is our g of x. So remember the way this rule works, if f of x is g of x to the nth power, f prime of x is n g of x to the n minus 1 power g prime of x. So here we got to be careful because now we have to differentiate log 3x, not just log x, but log 3x. Now, the 3 is just a constant. So what you can actually do, what you're going to end up needing here is 3x in the denominator. The numerator will be the derivative of this expression, which is 3. And so it'll end up, interestingly enough, with just 1 over x. So then we can come down here and say that f prime of x. Now remember here, 2 is n. G of x is log 3x. We raise that to the 2 minus 1 power, and then we multiply this by 1 over x from up here. And so we ultimately end up with 2 log 3x all over x. All right. So here the challenge was to identify g of x. You could try the other approach where g of x is 3x, but it's a little bit more straightforward to do it this way, because then we have the power rule, the generalized power rule that we can lean on. But even then, like we saw here, we still need to figure out the derivative of log 3x. Okay, so that would be 3 over 3x, which reduces to 1 over x. And then we can use the generalized power rule and we're all set. Okay, how about this one? This is the one, now remember, we introduced this method of substitution. So basically, whenever you see a couple of different polynomials or expressions in the same integral, where let's say the powers of x are only different by 1. Like here, for example, we have x squared in the denominator and just plain x in the numerator. That is kind of a sign that this might be a good opportunity to use the method of substitution, because if you choose u to be the expression with the higher value of the exponent, that makes it much more likely that you'll be able to find du. So here, now you can see that we have x dx, but not 2x dx. So here's what we're going to do. And now, of course, what I did was I multiplied the numerator by 2 and multiplied the whole expression by 1/2. I haven't changed anything, but all of a sudden, look what I have. This is my du. And down here is my u. And that's just 1/2 log absolute u plus c, which is just 1/2 log absolute value x squared plus 4 plus c. Right, so we've seen this before. I mean, when you try the method of substitution, the challenge often is making sure that you have both u, some function of u in there plus du. And if du isn't quite where you need it, as long as the problem is that you're missing a constant, you can supply your own constant and make it work. Okay, you just have to be careful, choose the right constants, and also make sure you don't affect the value of your results. Like here, we multiply by 2 and essentially divided by 2, or multiply by 1/2. And that, of course, didn't affect our results. So that's our final answer. So that wasn't too bad. All right, now, once again, let's go back and revisit these properties. You never know when you might need them. Now, again, often these properties are helpful because they can just help us reduce the complexity of a problem. So let's go back here. And here's a simple case. Imagine you were confronted with this catastrophe and you said, wait a minute, I know what I can do here. Obviously, 3 squared is 9. And if you remember, we have this property, the exponential, the power rule for logarithms, which means that this is the same thing as, well, actually, this negative is out here. So just this term by itself. Oh, wow, I've never seen that before. What did I do to get that ruler on there? Well, I'll investigate that later. Oh my God, I don't think it wants to come off. I swear to, I've never seen that before. I'm sure it has something to do with my tablet. I must have leaned on the wrong button or something, but now I don't know what to do. Well, I'll just move you out of the way. I'll figure that out later, that's for sure. But anyway, yes. So what just happened here? Let's try that again. Anyway, so the first one is clearly 3 squared. And this piece by itself, 2 log 3, is the same as log 3 squared. Or you can just write it as log 3 squared. It's understood that the entire expression is being squared. And then here, now, log 1/3. Remember, 1/3 is 3 to the negative 1. Now, that isn't really absolutely necessary because you can see here that these two actually cancel each other out. Let me get rid of that. Yeah, those two cancel each other out. And so you're just left with 3 to the minus 1, or you can rewrite that as negative log 3. Okay, so you're done. I think you'll agree that negative log 3 is a lot neater and easier to work with than all of this. Now, at this point, we didn't actually have an example with an integral, but you can easily imagine that if you had a very, very messy integral involving a bunch of logarithms, you might be able to streamline it a little and make it possible to use some of the rules that we've learned and make our lives a little simpler. You just never know. So it's important to understand these properties and be ready to use them if an opportunity presents itself. Now, E, we already know that E is the base of the natural log. Okay, but in terms of area, what we're seeing here is that based on that same curve, y equals 1 over t, the area between 1 and E, where E is about 2.78, is equal to, as we saw earlier, log E. But if you integrate this function, let's see what happens here. Let's prove this ourselves. This is equal to t to the minus 1 dt. Okay, what do we have here? Oh man, this is proving to be messier than I anticipated. Hold on one second. Oh, no, there's a mistake here. This should have been negative. Oh, no, I was right the first time. It is positive. Okay, that's interesting. Oh, I know what the problem is. No, sorry, my fault. I applied the wrong rule. No, let's try that again. I should use the power rule when I shouldn't have. All right, I forgot. That's the exception. T minus 1 is the one we're not allowed to use. So let's try that one again. No wonder it didn't work. All right. So the integral of t to the minus 1 dt is the natural log of absolute t. And we'll evaluate that from 1 to e. Now, e is a positive number. We don't need the absolute sign. Okay, that's much better. Natural log of e is just 1. And the log of 1 is 0. So yeah, it works. We're good. In other words, what this is showing us, the graph is saying, listen, as we saw before, because we're looking at the curve or the function y equals 1 over t, the area between 1 and any other point under that curve between 1 and some other value x equals the natural log of x. Whatever x is, this region represents its natural log. So here, we chose as our e or x the value e. So if this is log of e, well, log of e is just 1 because the base is e. So in other words, what they're saying is that this is one way of defining e as that area under that curve between 1 and e. In other words, e is the range, the upper limit of integration such that that area equals 1. Now, by the way, I know somewhere along the way, it turns out that E is also defined in terms of limits. And so I just want to throw it out there right now. There's 2 equivalent ways of doing this. So here we go. E can be defined in multiple ways, as you can see now, but this is one that's going to actually prove to be very, very useful in the next section of this chapter. In particular, it'll help us when we start looking at interest rates and how to calculate, for example, how much an investment will be worth in the future. So in that case, the limit definition is going to come in very handy. But this is where E is actually defined, at least in terms of limits. Okay, so we can define it in terms of integrals up here, as we did, but we can also define it in terms of limits. And, of course, the one you'll use is the one that you need for a particular circumstance, depending on what you're trying to solve for. But it's good to know that we have multiple ways of defining the same concepts so that we can use whichever one helps us the most. Now, exponential function, we also have properties here that we need to be aware of. E to the p power times e to the q. Again, p and q are any real numbers. R is a rational number. The exponent is it's e to the p plus q power. Over down here, since we're dividing, we end up with e to the p minus q. And then here, just like with the logs, well, actually not like the logs, here e to the p all raised to the r power is e to the p r power. By the way, I just want to mention that these properties will hold no matter what real number you have. In other words, it's not just for e. If you had this, any x, as long as it's a real number, any real number, and then here's the same thing, x to the p power all raised to the r power is x to the p r power. Okay, so now the reason why I mentioned that is because what if we run into a case like this? Now that looks like a mess. And remember, up to this point, we haven't really done any integrals involving products. They can be insanely messy. And, you know, of course, you'll see some of that in Calc 2, but for Calc 1, ideally, what you'd like to do is simplify these as much as possible before you try to apply any of the rules. So here we have a good example of this because all we have to do is combine, because e is the same base in both numbers, you can just add these together. And you might recall that when you're taking the derivative of e to the g of x, you have e to the g of x, g prime of x. Okay, this is a special version of the chain rule. But remember too, we had something like this. We just ended up with e to the x. And again, even though it might not seem like it, in principle, we were using this rule because if you let g of x be x, g prime of x is actually just 1. So in other words, you don't need the 1 here because it just drops out. So the derivative of e to the x is just e to the x, but for anything more complicated than that, you need to use the full chain rule. So here, then, by rewriting our expression like this, we know now that g of x is 3x plus x squared, and g prime of x is 3 plus 2x. And so we're all set because when we plug them in, well, there it is, okay? In other words, this is e to the g of x, and this is g prime of x. And that's it, we're done. Okay, now let's try a fairly scary looking integral with, again, our old friend, the method of substitution. So again, the challenge with these things is always trying to come up with what should we call u? So you would think that, you know, maybe u could be e to the minus x squared, but then what happens? Then you would need for du dx, you would have e to the minus x squared times minus 2x. We don't have that, do we? No, so that clearly can't be right. So let's try this instead. Let's try setting u equal to the exponent. That might work. And then du would be minus 2x dx, but we don't exactly have that. We have 2x dx, but not negative. So let's do this. And while we're at it, let's rearrange it a little. So there we go. We have minus integral e to the u du. And that's it, we're done. And of course, as always, you can try to go back and if you apply the chain rule here, Well, why don't we do this? Let's differentiate a result and make sure that it worked correctly. So in other words, if you started with, you want to take the derivative of minus e to the minus x squared. You don't need to worry about the constant because the derivative is just 0. So let's just write this piece in. And if you notice again, this is e to the g of x, although there is a negative here. So you can factor that out if you want to. Might be easier. Okay, so let's do that. G of x would therefore be minus x squared. G prime of x is minus 2x. So we're going to have minus on the outside, e to the minus x squared times minus 2x. And these two negatives cancel each other out. And so that's what we started out with. And so that proves that we've done this correctly. It's always nice to double check. And of course, you can always lean on our friend Symbolab too, if you want to. All right, now here's some interesting results involving logs and exponentials. Some that you might surprise you to no end. For example, and again, it's good knowing these because that will help us maybe rearrange or simplify an integral that's giving us a lot of trouble. It turns out that any a, as long as it's positive, as long as x is real, a to the x equals e to the x log a. Interesting. And you can see why that might come in handy. Not always, of course, but there may be cases where you've got a very complicated integral, and knowing this could help things, smooth things along. Okay. Then there's more. Let's take a look at some of these others. The derivative of a to the x is a to the x log a. Okay. And that log a is there because the base is not e. If it had been d dx, e to the x, as you know, it would simply be e to the x. So the fact that this is not e to the x, but a to the x means we need this log a. And then, as we've just seen, here we have e to the g of x, g prime of x. But because this is a now, the result is similar, except for this. This is the extra bit we need because we do not have the natural log. Other than that, they're the same. Oh, there's some more here. Let's take a look. The integral of a to the x dx is 1 over log a to the x. Okay. And again, the only reason this is here is because instead of e to the x, you have a to the x. The derivative of log a of x is 1 over x log a. And again, this is only necessary because this is the log base a. And then again, same thing down here. Okay, so that log a comes in because we're dealing with either a to the x or the log base a. Okay, instead of the natural log. All right, so when is that going to help? Well, let's take a look at this. Now, this one requires a little bit of cleverness. Oh, well, now we're asking for trouble here. No, we're not. I'll tell you why. Because oh, that's interesting. So, for example, what if x is 3? 4 cubed, according to this, is equal to 2 to the 6th power. Is that right? Well, take out your calculator. This is 64, and this is 64. So why don't we try that here? And guess what that means we can do? And if you notice, in this case, A is 2. So what rule are we looking at here? Let's go back. There it is. This is what we have. Slide this down here. Oh, actually, no, this one, the exponent this is the wrong one because the exponent is a function of x. Let's go grab the right one here. Yeah, here it is. Okay, I have it. It's this whole thing. Okay, so you're going to have g of x here. Which implies that g prime of x, I'll move it over here, is 2 plus 2x. And the rule that we need, again, is this one. So given this rule, and we can see for ourselves that a is 2, that implies that this derivative must be 2 to this power log 2, and then the derivative of g of x, g prime of x, is 2x plus x squared. And of course, you can simplify this a little. Well, not really. But yeah, that's your final result. Okay. Oh, I just realized I copied the wrong thing. Sorry, hold on one second. Right here, this is g prime of x. I copied the wrong thing here. This is g of x. G prime of x is 2 plus 2x. There we go. Now we're good. Okay. Man, what else? Oh, look at this one. Log base a. It's not a natural log. What rule do we need? This one. Okay, in other words, we have a log that's not natural log, and on top of that, it's applied to not just x, but a function of x. So let's say that a is 8, g of x is, of course, 7x squared plus 4, which means that g prime of x is 14x. So we're going to wind up with 14x over 7x squared plus 4. And then we'll have the natural log of 8. Okay, that wasn't so bad. Now, this next one is really a bit of a challenge because there's an identity involved here. Very interesting identity. Oh, 4 to the x to the 4. What are we supposed to do with that one? Well, here's what we're looking at. Anytime you have any real numbers where a cannot be 0, because that would make, well, actually, it's even more stronger than that. A has to be strictly positive. And then, let's see. Actually, so does B for that matter. So what is this getting us? Well, if you let A be 4 and B is x to the 4th power, then this is the same as taking the derivative of e to the x to the fourth power log 4. Now, log 4 is just a constant. Also remember that when you take the derivative of e to the g of x, you're going to wind up with e to the g of x times g prime of x. Well, in this case, g of x is all of this. And don't forget that log 4 is a constant. So we're going to use the power rule. We're going to have 4x to the third times log 4. So, hold on. All right, so what we're going to, oh, Jesus. Hold on. No. Yeah, I've had this problem before in this class. I know this tablet, the marker has this button on the side. And if your finger brushes up against it, you're going to have this messy trail all over the place. I have no idea why they put that in there. Who would actually want to use it? I don't know. So anyway, based on what we're seeing here, we should have e to the, we can write this as e to the 4x4 if we want to. We could actually, you know, I'll tell you what, let's leave it like this. Let's just leave it as x to the 4 log 4. And then g prime of x here would be 4x cubed log 4. And there's really not much simplification that you can use here. Okay. Now here's another one. Oh, what are we supposed to do now? Well, all right, the surprise has already been spoiled for you. You can see that we can rewrite it, move the 3 outside because it's a constant. And then you have 2 to the negative 3x power. So this is one of these a to the g of x problems. So where g of x will be the negative 3x. And of course, g prime of x will simply be negative 3. So let's go grab that rule. Oh, I see what's happening. We're not going to use a rule. We're going to use the method of substitution. Oh, all right. You know why? Because if you let u be minus 3 to the x, never mind the g's right now. There's no, the reason why I realized it right away is because there was no rule for this case. Instead, what we're going to do is we're going to use method of substitution. You can tell this must be it because you can see we've got 3 dx. We need to supply the negative. Oops. 2 to the minus 3x. And you can rewrite this if you want as 2 to the minus 3x minus 3 dx, which means we have integral of e to the 2 to the u power du. Now, all of a sudden, we do have a rule that works. Okay, if you look back here, we had a rule for the integral of a to the x. Where is it? There it is. Okay, so the method of substitution was needed to bring this into a format that we can use with one of our existing rules. So we have, instead of a to the x, we have 2 to the u, but it's the same thing. So we'll have 1 over log 2 2 to the u plus c. Now, of course, we don't forget to substitute for u. Oh, and also there's a negative here. I almost missed it. And in this case, we define u to be negative 3x. There you go. Okay, that was that. All right, so 6a is done here. Now, I just want to give you a forecast. Oh, you know what I just realized? I didn't even see this. That mysterious ruler is coming from here. It has nothing to do with my my Wacom tablet. It was up here all that time, and I just didn't even see it. I had no idea that that was even there. Not sure what we're supposed to do with it. Doesn't seem to want to move for me. Jesus. So I'm just going to turn it off. I've never seen that before. All right. Anyway, I just want to give you a forecast of what's coming in 6b. We're going to be looking at actual applications here, some very interesting ones, as a matter of fact. We're going to be looking at the concepts of growth and decay. And just a quick overview here, the growth can be used in lots of applications, really, but in particular, potentially the growth of a population, growth in the value of an investment, and then the decay can be used for the half-life of radioactive elements. You might remember that from high school. You learned how to tell how long it would take before all the radioactive elements in, let's say, a bar of uranium would take to turn into lead. And then carbon dating. Of course, every crime show ever made uses carbon dating to tell how old a murder weapon is, or whatever the case may be, because it's, you know, it's well known what the half-life of carbon-14 is. And so you can tell how old something is by looking at how much carbon it's 14 is still in it. So anyway, so we'll be doing that. And we'll be focusing our attention again on the exponential function, because it's awfully, awfully useful in a lot of real world applications. Okay, so the next recording will be chapter 6b. And again, it'll focus on applications of growth and decay, which I think you'll find to be extremely interesting. There won't be any new rules in here. It'll just be all applications. Okay, so for now, we'll stop here. We're done with 6a, and then the next recording will be all chapter 6b. Okay, so I wish you a good night.